Hello, today we'll be reviewing the solution for the problems that were included in exam number 2. So let's get started with that. Well, first, this is the first problem that we have for the exam. The general idea is that we are working with the concept of the Marriott bottle, and we will have to find the outlet velocity for the conditions that are present in this problem. So our first step is to determine the uncertainty that we are working with. The problem is mentioning that we are using a chronometer and it has an uncertainty of 100 of a second. So 100 of a second is indicated by this notation. This is the tenth of a second and this is the hundredth of a second. Now, for the uncertainty, we have to remember that we are working with half of the minimum scale of the device we are using to measure. So the uncertainty for this problem will be 0.005 seconds. And this is the uncertainty that we will work with for this initial part of the problem. And now for section V, where we have to determine the inlet velocity. To obtain that, we have here an equation with the respective values. As we see here, we have uncertainty. This uncertainty is the one that we determined in the first section, so we have to replace that first. Now we have our equation complete. We can proceed to calculate the inlet velocity here. And for this, we are gonna use the fast rules for uncertainties. So our first step is to reduce this section to one term with the respective uncertainty. So let's go with that first. The quick rule for subtractions indicates that the main measurements will follow the operation indicated here. So we are gonna subtract both quantities. Here our result is 0.01. And now we have to determine the uncertainty. Here the fast rule indicates that for addition and subtraction, we have to add the uncertainties. And our result is 9 times 10 to the power of minus 4. Here we indicate this result in scientific notation, so for our convenience we will have to indicate this value in scientific notation also. So now our first equation becomes this. Now that we have this, we have to use the quick rules for divisions. And for divisions, we have to make a division between these two terms, and this will be a sum of both percentage of uncertainties of these both quantities. First, we're going to make a division. This is our result for the division with the respective units. Now we proceed with percentage uncertainties, and for that we have to remember how to calculate them. So first we take the uncertainty, and we have to divide with the main measurement, and the result times 100. And we have to add this to the other uncertainty. Following the same procedure, and the individual percentage uncertainties are 9% plus 0.1%. We add 9% to 0.1 and we obtain 9.1%. Now, since we have to state this uncertainty in as an absolute value, we multiply the percentage uncertainty with the quantity we obtain from the division, which is this one, or in other words, the 9.1% of 0.002. And this will give 1.82 times to the power of -4. Now we can state our complete result of the inlet velocity as 0.002 minus plus minus 1.82 times 10 to the power of -4. Now here is our final result for the inlet velocity. We don't round yet because we still have some calculations left, and the rounding is our final step for the problem. We only have to make sure that this power is matching the same order of magnitude in this quantity, so we can rewrite our value as the following. And this is our inlet velocity stated correctly. Now finally we have to find the outlet velocity with its respective uncertainty. For that we also have already an equation with the experimental values obtained, and here we are using the inlet velocity we calculated in the previous section. So our first step is to use the previous data we obtained to use for the calculation. By using the fast rules for multiplication, we have to remember that our main quantities are multiplied, and in the case of uncertainties, they are summed by using the percentage uncertainty of both. So our first term in this division has a result of 22.62 times 10 at the power of minus 6. And now we have to calculate the uncertainty of this quantity. Remember that for the uncertainties, we have to divide the uncertainty with the main value, and the result is multiplied with 100. In the case of the second uncertainty, we have to remember that we already calculated that and we obtained that it was 9%. This gives a result of 0.7957% plus 9%. This is a total uncertainty of 9.79%, and this percentage can be reduced to 9.8. Now we can rewrite our equation as follows. Note here that we are keeping the percentage uncertainty, and that is because we will use it for the division. Remember that the quick rule also uses the percentage uncertainty for both measurements, so we will have to calculate this uncertainty with and transform it to a percentage uncertainty. The outlet velocity is 0.8078, and now we have to determine the value of the uncertainty. The result is 9.8% plus 17.8571%, and the total percentage uncertainty is 27.65%. Remember that percentage uncertainties don't have a proper rule to determine how many decimals we have to count, so we can round whenever we decide that is needed. So let's proceed with this value. Our outlet velocity is 0.8078 plus minus 28% of uncertainty, which can be rewritten as we take the 28% of the main measurement, and our final outlet velocity is 0.8078 plus minus 0.2261 meters per second. Since this is our final result for the exam, we can now round our values. So .2261 becomes 0.226, 0.226 becomes 0.23. This becomes 0.2, and this is our last significant figure, and it is not 1, so now we have to match the same order of magnitude for this quantity, which will give us 0.8 plus minus 0.2 with an error of 28%. And this will be our last answer for the problem using fast rules. Some of the data we had will be the same. For example, the first uncertainty that we determined, and the equation that we had for the inlet velocity remains the same before calculation. Now that we have our original equation, we proceed to solve it. We have to remember that the equation that we have to follow for calculating uncertainties using the good rule for addition and subtraction is the following. It is the square root of the sum of the squares of both uncertainties. Now that we know this, the rest of the procedure remains the same. Here we have a subtraction of our two main measurements. This is the same value we obtained before, and now the new value that we will obtain is the uncertainty for this quantity. The result is 6.4 times 10 to the power of 4, and the inlet velocity is rewritten as 0.01 plus minus 6.4 times 10 at the power of 4, and the rest remains the same. The next step is division, and for a division we maintain a similar rule that we had, but in this case we are working with percentage uncertainties. Our main value is 0.002, and the uncertainty is determined by the following equation. The percentages are obtained in the same way. We have to divide the uncertainty with the real value, and that is multiplied by 100. The value for the uncertainty that we determine is 6.4%. And now the inlet velocity is 0.002 plus minus 6.4. Stating this value with an absolute uncertainty, we obtain 0.002 plus minus 1.28 times 10 at the power of minus 4. Now, to match the same power that we have here, we write again our equation as 20 plus minus 1.28, all of this times 10 to the power of minus 4. And this is our new value for the inlet velocity in the Marriott's bottle. Continuing with the section number 2, we remember that we had an equation that determined the outlet velocity, in which we had to use the area of the inlet times the velocity in the inlet and the area of the outlet. All of these values were provided. The only one that we have calculated is this one. So replacing, we have the following equation. This is the new equation that we have to solve. So now, for this section, we have to use the rules that are appropriate for multiplication. These rules are similar to the one we used for division, which is this one right here. The main difference is that we have to use the percentage of the uncertainties. So our main measurement is 22.62 times 10 at the power of minus 6. And for the uncertainty of this quantity, we obtain that the percentage uncertainty for the first term is 6.45%. Now, the outlet velocity is determined by the following. First, we do the division of the terms. This gives 0.8078, and the uncertainty for this quantity in percentage is now our new uncertainty is 18.98%. Which becomes 0.8078 plus minus 18.98%. And if we want to write this in as an absolute uncertainty, we multiply the percentage with the original quantity. So our new value for the outlet velocity is 0.8078 plus minus 0.1533 meters per second. And now the last step to do is to keep both measurements to the same order of magnitude, and we have to keep the uncertainty to the first significant figure. .1533 becomes 0.153, 0.8078 plus minus 0.15, and we cannot round more because one cannot be our only significant figure, so we keep both, and Using the same order of magnitude, we obtain 0.81 plus minus 0.15 meters per second. This has an error of 19%. And as we can see here, we have less error. So in the case that we need more precision with our values and our calculations, we will have to use more complex equations to obtain the correct uncertainties. And for the exam number 2, that's it. Thank you.